Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches of the outer solar system, where a visitor from interstellar space moves through darkness, pushed by forces too subtle for human hands to feel. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The discovery comes on a night like any other night. Automated telescopes sweep the sky in predefined patterns, their cameras clicking open and shut with mechanical patience, recording star fields in exposures measured by seconds. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, operates from twin observatories in Hawaii, scanning for objects that move against the fixed backdrop of distant suns. Most nights yield asteroids, familiar rocks in predictable orbits. Most nights the software flags a few dozen candidates, cross-references them against catalogs, dismisses the known, retains the new. Most nights nothing particularly unusual appears. On this night in early 2024, a faint smudge registers in the data stream. It moves, not with the gentle drift of a main belt asteroid, not with the leisurely arc of a Jupiter Trojan, but with velocity that seems wrong somehow, too urgent for the outer solar system's usual rhythms. The automated pipeline measures its position, waits 6 hours, measures again. The displacement exceeds expectations. Preliminary calculations suggest an orbit that does not close, that does not return, that opens into hyperbolic geometry and keeps opening. The object receives a provisional designation, a string of letters and numbers that will change once confirmation arrives. Observers at other facilities receive alerts. Can you see it? Can you measure it? The night sky cooperates, cloudless over Chile, over Arizona, over the Canary Islands. Telescopes slew to coordinates, exposures begin. Photons accumulate in sensor wells. Yes, they report. We see it. We confirm the motion. The mathematics agree. Within 72 hours, the orbit becomes clear enough to declare with confidence this object originates from interstellar space. Its velocity relative to the Sun exceeds escape velocity. It arrived from elsewhere, from the spaces between stars, carrying momentum inherited from its birth cloud and from gravitational interactions no one witnessed. It will pass through the solar system once, only once, and depart again into the galaxy's slow circulation. It will not return, not in 1,000 years, not in 1,000,000, not ever, barring some catastrophic encounter that rewrites physics. The discovery makes a small ripple in astronomical circles. Not the first interstellar visitor, that honor belongs to one I/Oumuamua. Detected in 2017, that strange elongated object that tumbled through the inner system and vanished before anyone could study it properly. Not the second. 2I/Borisov arrived in 2019, a more conventional comet with a visible tail, behaving predictably, confirming that interstellar objects need not be mysterious. This new visitor becomes the third confirmed, designated 3I/Atlas, once the International Astronomical Union processes the paperwork. The third known traveler from beyond. Already, even before detailed observations begin, the object presents a quiet puzzle. It shows a faint coma, a diffuse cloud of gas and dust barely visible in deep exposures. This suggests activity, sublimation, volatile ices transitioning to vapor under solar heating. Comets do this. Comets have done this for billions of years, whenever their elliptical paths carry them close enough to the sun's warmth. But 3I/Atlas lies beyond Jupiter's orbit when first detected, where solar radiation barely whispers, where temperatures hover near the threshold, where even carbon dioxide should remain frozen solid. Yet it outgasses anyway. Something escapes the surface. Something leaves the nucleus and expands into surrounding space, scattering sunlight just enough to create that faint halo in the images. The coma does not rage or billow. Nothing dramatic occurs. No sudden brightening, no jets visible to Earth-based instruments, just a quiet, persistent leak of molecules. A gradual unwinding of volatile inventory accumulated across light years and eons. Observers request telescope time. Proposals circulate. How bright will it become? How close will it approach? The trajectory models predict a perihelion passage, closest approach to the Sun, still outside Earth's orbit, still in the realm where distances feel abstract, where astronomical units pile up faster than intuition can follow. Not a close encounter by any standard, not a spectacle for casual skywatchers, an event for specialists, for those who measure photons with patient instruments and derive meaning from datasets that would look like noise to untrained eyes. The name itself carries a certain poetry, unintentional and bureaucratic. Atlas, acronym and mythological echo. The Titan condemned to hold the celestial sphere. Here the name labels a survey system, cameras and computers and alert protocols, but the resonance lingers. This object, this visitor, carries no burden except its own momentum and the subtle forces that act upon it. It holds nothing. It supports nothing. It simply passes through, indifferent to names, to observation, to the fact that one species on one small world has noticed its transit and assigned it meaning. In the first weeks after discovery, the observations accumulate slowly. The object remains faint, magnitude 16 or 17, requiring exposure times that test the limits of smaller telescopes. Large observatories contribute when their schedules permit, squeezing 3I/Atlas between exoplanet transits and supernova follow-ups, and the 1,000 other targets competing for mirror time. Each observation adds a data point. A precise measurement of position against the star field, a timestamp recorded in universal coordinated time. The catalog grows. The orbital solution tightens. Uncertainties shrink. And even in these early measurements, a subtle discrepancy begins to appear. The object does not move quite where pure gravitational models predict it should move. The deviations measure small, measured in arcseconds, fractions of a degree barely perceptible even in high-precision astrometry. But they persist. They accumulate. They suggest that gravity alone does not account for 3I/Atlas's trajectory, that something else pushes, pulls, nudges this visitor along a path slightly different from the one Newton's equations would draw. This surprises no one familiar with comets. Active comets always show non-gravitational acceleration. Outgassing produces thrust. Molecules leaving the surface carry momentum. And momentum conservation demands the nucleus recoil in the opposite direction. For bright, active comets close to the Sun, this effect can shift orbits by thousands of kilometers over weeks. For faint, distant objects like 3I/Atlas, the effect measures smaller but remains real. Detectable. Quantifiable. What remains unknown? In these first weeks is the magnitude of the push. How strong does the outgassing blow? In which direction does the thrust vector point? How will it evolve as the object approaches the Sun and solar heating intensifies? The observations continue. The measurements refine. The mystery persists, gentle and patient, waiting for more photons, more nights, more data points to accumulate in the archives, somewhere, far beyond human perception. 3I/Atlas continues its journey. It does not know it has been discovered. It does not know telescopes track its motion, that algorithms pass its reflected light, that researchers debate its composition and origin. It simply moves, pushed by starlight and by the quiet rocket effect of its own sublimation, following a trajectory carved by forces too subtle to feel, but strong enough. Over months and millions of kilometers. To measure, only took 4.5 billion years for anyone to notice. Only took the invention of CCD cameras, orbital mechanics software, and international astronomical networks. Only took one clear night in Hawaii and the patient accumulation of photons against a sensor. The Discovery image, archived now in digital repositories, shows nothing dramatic. A faint streak against stars, easily mistaken for noise, for cosmic ray hits, for any of the 1,000 artifacts that plague astronomical imaging. But the streak moved between exposures. The streak appeared again the next night. Displaced by exactly the amount orbital calculations predicted, the streak became a trajectory. The trajectory became a visitor. The visitor became 3I/Atlas, traveler from interstellar space, carrier of ancient ice, subject of quiet forces that push without sound through the darkness between worlds. The mathematics of orbital mechanics permits no ambiguity about certain facts. An object moving through the solar system follows a path determined by gravity, by the sun's mass creating curvature in space-time, by the inverse square law that governs how force weakens with distance. These equations, refined over centuries from Kepler's ellipses through Newton's calculus to Einstein's geometric insight, predict trajectories with extraordinary precision. They describe bound orbits, ellipses that close, that return, and unbound orbits, parabolas and hyperbolas that open into infinity and never complete a circuit. The distinction matters. A bound orbit means the object belongs to the solar system, captured by the sun's gravity, cycling through perihelion and aphelion in eternal return. An unbound orbit means the object passes through once only. A visitor with enough velocity to escape, to climb out of the sun's gravitational well and coast back into interstellar space. The boundary between these regimes lies at exactly escape velocity, the speed required at any given distance to break free forever. For 3I/Atlas, the initial observations reveal orbital elements that place it firmly in hyperbolic territory. Its eccentricity exceeds 1, the mathematical marker of an open orbit, not 1.01, barely hyperbolic, but something more decisive, a value that leaves no room for measurement error to drag it back into elliptical confinement. The semi-major axis appears negative in the calculations, another signature of hyperbolic geometry, a mathematical artifact indicating the orbit never closes. More telling still, the hyperbolic excess velocity, the speed the object will retain even at infinite distance from the sun, after gravity's influence fades to negligible values. This quantity measures several kilometers per second, fast enough to cross the distance from Earth to Moon in just hours, fast enough to traverse the orbit of Neptune in months rather than decades, fast by human standards, unremarkable by galactic standards, where stars orbit the Milky Way's center at 200 kilometers per second and random drift velocities between neighboring stars reach tens of kilometers per second. The trajectory reconstruction works backward as easily as forward. If the equations predict where 3I/Atlas will go, they also reveal where it came from. The orbital solution, refined through weeks of observations, indicates an origin roughly in the direction of the constellation Lyra, from the general vicinity where bright star Vega dominates the northern summer sky. Not from Vega itself. The geometry does not point that precisely. And the timescales involved mean 3I/Atlas could have traveled thousands of years while Vega moved through its own orbit around the galaxy, just from that general region of sky, that sector of the celestial sphere. How long has it traveled? The calculations cannot say with certainty. Interstellar space offers few landmarks, few events that leave measurable traces in an inert object's surface. The object might have wandered for 10,000 years, or a million, coasting through the near vacuum between stars, occasionally perturbed by distant gravitational encounters with other stars or molecular clouds, gradually accumulating cosmic ray exposure and micrometeorite impacts. Its surface, when spectroscopy eventually examines it, may carry clues, radiation damage, amorphous ice structures, chemical alterations that occur only over extended timescales. But these clues require interpretation, models, assumptions about initial conditions no one witnessed. What the mathematics reveals without ambiguity is the trajectory through the solar system itself. The object approached from above the ecliptic plane, the disk where planets orbit, entering the sun's gravitational influence at a steep angle, not perpendicular, not a plunge straight through, but inclined enough that its path cuts across the orderly arrangement of planetary orbits rather than threading between them. The geometry suggests 3I/Atlas will sample different distances from the sun as it passes, approaching close enough for solar heating to matter, receding again before any dramatic warming occurs. Perihelion, the closest approach, lies scheduled for several months after discovery. Positioned somewhere in the inner solar system, but not threateningly close. Not Venus grazing, not sun skimming. The exact distance depends on those non-gravitational forces beginning to manifest in the observations. Pure gravity would place perihelion at one location. Outgassing thrust shifts it slightly, pushes the object into a different trajectory, changes the geometry by amounts too small to see with unaided eyes, but large enough to measure with modern instruments. Astronomers construct models. Input the observed positions. Let software iterate towards solutions that best fit the data. The models include gravitational effects from the Sun, from Jupiter, from Saturn, the massive planets whose influence extends across astronomical units, whose tidal forces perturb even distant visitors. They include relativistic corrections, tiny adjustments Einstein's theory demands, effects that matter when precision reaches arcseconds, and they include non-gravitational terms, placeholder parameters representing forces the equations cannot derive from first principles, forces that depend on the object's composition. Rotation, thermal properties, surface activity. The non-gravitational parameters appear in the models as accelerations, small vectors pointing in various directions, magnitudes measured in tiny fractions of Earth's surface gravity. These accelerations might point radially from the Sun, representing symmetric outgassing. They might point tangentially, representing asymmetric jets or rotation-driven activity. They might point normal to the orbital plane, representing some peculiarity in how the surface releases gas. The models test different configurations. Compare predicted positions against observed positions. Calculate residuals, the differences that remain unexplained. For 3I/Atlas, the residuals show structure. Not random scatter, not noise, but systematic deviations that grow larger as the object approaches the Sun and solar heating intensifies. This pattern confirms active outgassing, confirms that volatiles sublimate and escape, confirms that the rocket effect operates as theory predicts. The magnitude of the effect remains uncertain in these early weeks, but its existence seems clear. Written in the astrometric data like a signature in gravitational ink. Other observers pursue different measurements. Photometry tracks, brightness changes, looking for variations that might indicate rotation, might reveal an elongated shape tumbling through space, might suggest surface heterogeneity with bright and dark regions. The light curve shows scatter, shows night-to-night variations, shows hints of periodicity that could mean rotation periods measured in hours or days. Nothing definitive yet. Nothing that pins down the nucleus size or shape with confidence. Just suggestions, possibilities, patterns that need more data to confirm or refute, spectroscopy begins as well. Though the object's faintness challenges even large telescopes, the reflected sunlight carries fingerprints, absorption features where molecules in the coma absorb specific wavelengths, emission lines where solar ultraviolet radiation excites gases to fluoresce. Early spectra show water signatures, the expected H2O bands that dominate most cometary emissions. Carbon dioxide appears as well, CO2 absorbing in the infrared, sublimating even at the cold temperatures beyond Jupiter where solar flux barely warms surfaces above 100 Kelvin. The detection of organics requires deeper exposures, more sensitive instruments, careful background subtraction. Hints emerge: possible CN emission, maybe C2, organic radicals created when solar radiation breaks apart more complex molecules. These detections remain tentative, requiring confirmation, requiring more photons and more telescope time than observatories can easily spare for a single target. The observers submit proposals, request hours on larger mirrors, argue for the scientific value of characterizing an interstellar visitor's composition before it fades from view. Only took humanity 400 years to develop the mathematics that describes these orbits. Only took 3 centuries more to build instruments sensitive enough to detect objects this faint at this distance. Only took the invention of digital sensors, precise timekeeping, international collaboration to make discoveries like this routine rather than miraculous. The orbit exists independent of observation, carved through space-time by gravity and momentum. But knowing the orbit, measuring it, predicting where 3I/Atlas will appear next week or next month, that requires infrastructure, requires centuries of accumulated knowledge, requires software running on computers that process numbers faster than neurons fire. Somewhere in the outer solar system, 3I/Atlas continues its inbound journey, unaware that its trajectory has been calculated, that its hyperbolic excess velocity has been measured to 3 decimal places, that researchers debate whether its perihelion distance will place it closer to Earth's orbit or Mars's. The object moves, pushed by the sun's gravity, pulling it forward and downward into the inner system, pushed as well by photons and by its own outgassing, forces that act without consultation or permission. The mathematics describes what happens. The observations confirm the mathematics. The mystery lies not in whether non-gravitational forces act, but in their precise magnitude and direction. Details that wait for more data, more nights, more patient accumulation of measurements. The International Astronomical Union maintains protocols for naming celestial objects, bureaucratic procedures refined over decades to impose order on the sky's taxonomy. Asteroids receive numbers and optional names. Comets receive designations indicating discovery year and orbital type. Interstellar objects, being relatively new to the catalogue, required new conventions, new categories, new prefixes to distinguish them from the solar system's native population. The prefix I denotes interstellar, a simple letter, unambiguous, immediately informative to anyone who reads astronomical circulars. The number preceding it indicates sequence of confirmation. 1, I for the first recognized interstellar visitor, 2I for the second, 3I for the third. After the prefix comes the discoverer's designation, the survey or observatory that first reported the object. Thus, 3I/Atlas, the third confirmed interstellar object, discovered by the asteroid Terrestrial Impact Last Alert System. The name carries no poetry beyond its components. Atlas, the survey. Named for mythological resonance, but functioning as pure acronym in daily use. The 3I prefix, numerical and categorical, sorts the object into its proper taxonomic bin. No grand title, no evocative label like ancient astronomers bestowed on comets, the Great Comet, the Daylight Comet, descriptions that conveyed spectacle and emotion. Just 3I/Atlas, functional identifier, database entry, catalog reference, Before this designation, the object carried a provisional name, a longer string of characters encoding discovery date and sequence within that date. These provisional names serve as placeholders, used in initial reports and circulars before the orbit receives sufficient confirmation for permanent naming. Most observers never bother learning provisional designations. Too many objects, too many strings of letters and numbers. Easier to wait for the permanent name or simply refer to the new interstellar object in conversation. The naming happens quickly once the orbit proves hyperbolic beyond doubt. Within a week of confirmation, the IAU's Working Group for Small Body Nomenclature reviews the case, verifies the discovery credit, approves the designation, 3I/Atlas enters the official catalog, databases update, papers in preparation adjust their abstracts to use the formal name. The object acquires permanence in the astronomical record, a fixed label that will persist in archives and references for as long as humans maintain such records. Only 3 interstellar objects confirmed, only 3 entries in this particular catalog. The rarity surprises some researchers. Though statistical models predict interstellar visitors should pass through the inner solar system fairly regularly, perhaps 1 per year within Jupiter's orbit, perhaps several per year if counting more distant passages. But detection requires the object to be large enough, bright enough, active enough to register against the sky's background. Most interstellar visitors likely pass unnoticed, too small or too dark or positioned where no telescope happens to look. 1I/. Oumuamua arrived first, announced in October 2017, a peculiar object that tumbled through the inner system and departed before anyone fully understood what they had seen. Its name, meaning scout in Hawaiian, acknowledged the discoverers at Haleakala Observatory. Its behavior puzzled observers. Elongated shape inferred from brightness variations, excess acceleration that suggested outgassing but no visible coma, spectrum showing no obvious volatiles. Debates continue about its composition, its origin, whether it represents a typical interstellar traveler or some unusual outlier. 2I/Borisov followed in August 2019, discovered by amateur astronomer Gennady Borisov using a telescope he built himself. This object behaved like a conventional comet, bright coma, visible tail, spectra showing water and carbon monoxide, activity consistent with solar heating. Astronomers felt relieved to find something comprehensible after Oumuamua's strangeness. 2I/Borisov confirmed that interstellar objects need not be mysterious, that other planetary systems produce comets similar to our own, that the galaxy contains familiar chemistry repeating itself across light years. Now 3I/Atlas joins the catalog. Neither as strange as Oumuamua nor as conventional as 2I/Borisov. It shows a coma, confirming volatile content. It undergoes non-gravitational acceleration, confirming active outgassing, yet it remains faint, distant, subtle in its manifestations. No dramatic tail develops, no sudden outbursts occur, just steady. Persistent sublimation, enough to create measurable effects, but not enough to produce spectacle. The catalog of 3 objects permits few statistical conclusions. Too small a sample to derive trends, to calculate occurrence rates with confidence, to determine what fraction of interstellar visitors show cometary activity versus inert behavior. Each object represents itself, individual and particular, not yet subsumed into population statistics. Astronomers must wait for 4Y, for 5I, for dozens more detections before patterns emerge, before understanding deepens beyond case studies. Naming conventions extend beyond the primary designation. Observers sometimes refer to 3Y by shorthand, dropping the slash and survey name, just calling it 3Y in conversation. Papers might use Object 3I or the Atlas interstellar object, depending on journal style and author preference. The object itself, indifferent to nomenclature, continues moving through space under no name whatsoever, unnamed for billions of years before discovery, to be unnamed again once human civilization ends or forgets. The designation encodes information compactly. Anyone reading 3I/Atlas immediately knows third interstellar object discovered by Atlas survey. No need to explain further. No need to specify that it originated beyond the solar system. No need to clarify that its orbit is hyperbolic and unbound. The prefix conveys everything efficiently. A compressed packet of taxonomic meaning. Other naming systems exist in parallel. The Minor Planet Center assigns internal numbers for tracking purposes. Orbital databases use various identifiers to cross-reference observations from different sources. Each system serves its purpose. Each maintains its own logic. But for public reference, for papers and presentations and catalog searches, 3I/Atlas serves as the standard designation. The name that will persist in astronomical literature as long as such literature exists. Only took 3 confirmed detections to establish a naming convention for interstellar objects. Only took 2 decades of modern sky surveys, improving sensitivity and cadence, to reach this point. Only took the realization that interstellar visitors pass through regularly to prompt the creation of a separate taxonomic category, distinct from asteroids and comets native to our system. The names accumulate slowly, 1 per year or less, each designation marking a moment when automated systems or attentive observers notice something moving too fast to belong, something carrying velocity inherited from distant stellar neighborhoods. The name appears in observation logs now, in telescope schedules, in proposal titles requesting time to study this particular visitor. Observations of 3I/Atlas requested for nights of. Spectroscopic characterization of interstellar object 3I/Atlas. Non-gravitational acceleration in the trajectory of 3I/Atlas. The designation propagates through documentation, becomes familiar to researchers, enters the vocabulary of those who track small bodies moving through the solar system, somewhere beyond Jupiter's orbit. The object designated 3I/Atlas continues its journey, carrying no awareness of its catalog position, no knowledge that it has been named and numbered and entered into databases. It moves through vacuum, through photon flux, through gravitational gradients, responding only to physical forces, to momentum and energy conservation, to the deterministic unfolding of its trajectory through space-time. The name exists only in human records, only in the symbolic systems humans use to organize knowledge about the universe. The object itself remains nameless and unconcerned. Ancient ice and rock and organics continuing a journey that began light years away and will continue light years hence, briefly illuminated by one star's radiation, briefly noticed by one species capable of calculation and curiosity. Light carries information across interplanetary distances, photons traveling at their fixed universal speed, arriving at Earth-based telescopes after journeys measured in minutes or hours depending on the object's distance. Each photon interacts with matter before reflecting, absorbing and re-emitting at wavelengths determined by molecular structure, atomic transitions, electronic energy levels. These interactions encode chemical fingerprints, signatures unique to specific compounds, readable by instruments designed to pass light into its constituent wavelengths. Spectroscopy performs this passing, dispersing reflected sunlight through gratings or prisms, spreading the spectrum across detectors that measure intensity at each wavelength. The resulting data appears as a graph, brightness versus wavelength, showing peaks and valleys where emission and absorption occur. Interpreting these features requires matching observed patterns against laboratory measurements, against theoretical models of molecular transitions, against decades of accumulated reference spectra from comets and asteroids previously studied. For 3 I/Atlas, the first spectra arrived from large observatories with instruments sensitive enough to gather meaningful signal from an object this faint. The data shows sunlight's familiar continuum, the black body spectrum of a star heated to 5700 Kelvin, reflected from the object's surface and coma. Superimposed on this continuum appear absorption bands, specific wavelengths where molecules in the gas cloud absorb photons preferentially, creating dips in the measured intensity. Water dominates the spectrum, as expected for any active comet beyond the frost line where ice remains stable until solar heating drives sublimation. The H2O molecule absorbs strongly in several spectral regions, producing characteristic band structures that spectroscopists recognize immediately. The strength of these features indicates abundant water vapor in the coma, molecules escaping the nucleus at rates that can be estimated from the absorption depth and the geometry of observation. Carbon dioxide appears as well, CO2 producing absorption features in the infrared spectrum where water's signal weakens. This detection matters because carbon dioxide sublimates at lower temperatures than water ice, remaining active even when the nucleus surface stays too cold for water to escape efficiently. The CO2 detection confirms activity at distances where solar heating barely exceeds 100 watts per square meter, where surface temperatures hover near 120 Kelvin, cold enough to freeze air solid on Earth but warm enough, barely, to drive sublimation of this volatile compound. Trace organics show hints in deeper exposures, though the signal-to-noise ratio challenges confident identification. Possible CN emission appears, the cyanide radical produced when solar ultraviolet breaks apart more complex organic molecules, maybe C2, diatomic carbon, another photodissociation product. These detections remain tentative, requiring confirmation from multiple observations, requiring wavelength calibration accurate to fractions of a nanometer, requiring careful subtraction of atmospheric emission lines that contaminate ground-based spectra. The organic content interests astrobiologists and planetary chemists, not because it suggests life, these simple molecules form readily in non-biological settings, but because it reveals the chemical inventory of the interstellar medium where 3 I/Atlas originated. Molecular clouds between stars contain complex organic chemistry, synthesized in dark, cold environments through slow reactions on dust-grain surfaces. Objects condensing from such clouds inherit this chemistry, preserve it frozen in their ices, carry it across light years until solar heating releases molecules into space where spectroscopy can detect them. Dust complicates the spectroscopic analysis. Solid particles in the coma scatter sunlight without the sharp absorption features that gases produce, contributing a continuum signal that dilutes the molecular signatures. The dust-to-gas ratio, how much solid material escapes relative to vapor, affects the spectrum's appearance, makes abundance estimates uncertain. Observers attempt to separate dust and gas contributions by measuring at different wavelengths, by modeling the scattering properties of various grain compositions, by comparing observations taken days apart as the dust cloud evolves. The spectrum shows no obvious surprises, no unexpected molecules, no chemical anomalies that would distinguish 3 I/Atlas from solar system comets, water, carbon dioxide, simple organics, the same compounds found in comets native to the Oort cloud or Kuiper belt. This similarity suggests interstellar space and the outer solar system share chemical processes, share formation conditions, produce ices with comparable compositions despite their different gravitational allegiances. Yet subtle differences might exist, buried in the data below current detection limits. Isotope ratios, the relative abundance of deuterium versus hydrogen, carbon-13 versus carbon-12, could reveal different formation environments, different stellar neighborhoods with different nucleosynthetic histories. Measuring these ratios requires high spectral resolution, requires detecting weak isotope log features beside much stronger main isotope lines, requires observation time that exceeds what most facilities can allocate to a single transient target. The oxygen-forbidden lines appear in ultraviolet spectra obtained by space-based telescopes above Earth's absorbing atmosphere. These emissions arise when solar extreme ultraviolet radiation ionizes water molecules, producing O+ ions that fluoresce at specific wavelengths. The line strengths allow estimation of water production rates, how many molecules per second escape the nucleus, feeding the coma and creating the outgassing thrust that perturbs the orbit. Production rates measured in molecules per second sound precise but carry significant uncertainty. The calculation requires knowing the coma's extent, the excitation efficiency of solar radiation at the object's heliocentric distance, the velocity distribution of escaping molecules, the fraction of water that dissociates before spectroscopy detects it. Models make assumptions about these parameters, propagate uncertainties through the calculations, arrive at production rates accurate perhaps within a factor of 2 or 3, adequate for characterization, insufficient for detailed physical modeling. The spectroscopic data accumulates in archives, tables of wavelength versus flux, headers recording observation dates and instrument configurations and telescope coordinates. Future researchers might revisit this data with improved analysis techniques, might extract signals current methods miss, might discover subtle features that reveal details about composition or physical processes, or the data might sit unused, one more object among thousands. Spectra preserved digitally but never examined again after initial papers published their results. Only took 200 years to develop spectroscopy, from Fraunhofer's first observations of solar absorption lines to modern Echelle spectrographs resolving thousands of wavelengths simultaneously. Only took another century to extend spectroscopy into space, above atmospheric absorption, accessing ultraviolet and infrared regions impossible to observe from Earth's surface. Only took decades of laboratory work measuring molecular absorption coefficients, transition probabilities, excitation cross-sections, building the reference database that makes spectroscopic interpretation possible. The molecules themselves, escaping from 3I/Atlas's surface, carry no information about their detection. They expand into vacuum following thermodynamic principles, velocity distributions determined by temperature, trajectories determined by initial direction, and subsequent photon pressure. Some molecules photodissociate within hours, broken apart by solar ultraviolet. Others persist for days, drifting away from the nucleus, eventually dispersing too thinly to detect. None survive the journey back to interstellar space. The coma represents irreversible loss, inventory that will never recondense, chemistry that escapes the object permanently. The reflected light, traveling from 3I/Atlas to Earth, takes minutes or hours depending on distance. The photons detected tonight began their journey this morning, or yesterday, or last week, carrying information about conditions that already lie in the past. By the time spectroscopy measures water production rate, the actual production might have changed, might have increased as solar heating strengthens, or decreased as active regions rotate out of sunlight. Astronomy always observes history, always interprets light-delayed images of reality that continues evolving in the present, unknowable until future photons arrive. Beyond Jupiter's orbit, where the Sun appears smaller than a fingernail held at arm's length from Earth, solar radiation still carries energy, still delivers photons across the gulf of space at the rate of 50 watts per square meter. Not much compared to Earth's 1400 watts per square meter, not enough to warm surfaces above temperatures where breath would freeze instantly, but enough to drive processes, enough to push ice molecules from solid phase into gas without passing through liquid. Sublimation occurs when solid transitions directly to vapor, no melting involved, molecular bonds breaking as thermal energy exceeds the lattice binding energy holding crystal structure together, For water ice at low pressures, this transition happens at temperatures well below freezing point, around 170 Kelvin in vacuum, where atmospheric pressure cannot force a liquid phase. For carbon dioxide, the transition occurs even colder, near 150 Kelvin, CO2 sublimating more readily than water at distances where solar flux barely whispers. 3I/Atlas shows activity beginning at approximately 6 astronomical units from the Sun, about Jupiter's orbital distance, where solar radiation provides just enough energy to drive sublimation from surface layers exposed to sunlight. The process starts subtly, perhaps a few kilograms per second of volatiles escaping, invisible to most instruments, detectable only as a faint increase in brightness that might indicate a developing coma. Over days and weeks, the rate increases as the object moves inward, as solar flux grows, as surface temperatures rise degree by degree. The ice lies buried beneath dust in some regions, exposed directly to space in others, heterogeneous across the nucleus surface, depending on how impact gardening and previous sublimation cycles have rearranged material. Where dust covers ice, sublimation must penetrate the insulating layer, gas molecules diffusing through porous regolith before escaping to space. Where ice lies exposed, sublimation proceeds more efficiently, molecules leaving the surface at rates determined by temperature and vapor pressure equilibrium. The escaping molecules carry momentum, each H2O or CO2 molecule moving at thermal velocities around several hundred meters per second, directions random but averaging to a net outward flow away from the sunlit surface. This flow exerts pressure on the nucleus, tiny push, micronewtons of force distributed across active areas, but sustained over months, cumulative over the long, slow approach to perihelion. The nucleus, massing perhaps a few 100 million kilograms, uncertain, unmeasured, estimated only from brightness and assumed albedo, responds to this pressure by accelerating, changing velocity by millimeters per second, altering its trajectory by distances that grow with time. The rocket effect operates without combustion, without nozzles or thrust chambers, just the natural recoil from mass loss. Spacecraft engineers use similar principles deliberately, venting propellant to generate thrust, controlling direction and timing to achieve desired trajectory changes. For 3I/Atlas, the venting happens involuntarily, driven by solar heating rather than purposeful design, producing thrust that points in directions determined by which surface regions sublimate most actively. Asymmetry matters. If sublimation occurred symmetrically, if all sides of the nucleus lost ice at equal rates, the thrust vectors would cancel, producing no net acceleration. But real objects rotate, exposing different faces to sunlight as they spin, creating a time-varying thrust pattern that averages to some net direction depending on rotation axis, rotation period, distribution of active regions. The geometry gets complicated quickly, requiring models that track solar illumination across the surface, that account for thermal inertia and sublimation lag, that integrate thrust over rotation cycles for active comets near the Sun. These effects produce dramatic jets, visible plumes of gas and dust streaming from specific regions, fountain-like eruptions that telescope images capture in striking detail. For 3I/Atlas at 6 astronomical units, no jets appear, the activity too weak or too diffuse to concentrate into visible streams. Just a general haze, a symmetric-looking coma in low-resolution images, though high-resolution observations might reveal subtle asymmetries hinting at localized sources. The coma extends across thousands of kilometers, gas molecules expanding outward at their thermal velocities, gradually thinning as inverse square dilution reduces density with distance. Closer to the nucleus, the coma appears brighter, more molecules per cubic meter scattering more sunlight. Farther out, the brightness fades, merging imperceptibly into the background sky. No sharp boundary separates coma from space, just gradual decrease in molecular density. Asymptotic approach to the interplanetary medium's sparse population of hydrogen atoms and solar wind ions. Dust particles accompany the gas. Solid grains lifted from the surface when sublimation undermines their support, or when gas flow drags them upward faster than the weak gravity can hold them down. The nucleus gravity measures weak indeed. Perhaps a few 10,000ths of Earth's surface gravity, barely enough to hold regolith in place, easily overcome by gas pressure or by mechanical disturbances. Grains that escape join the coma, reflecting sunlight more efficiently than gas molecules, contributing disproportionately to brightness despite comprising only a small fraction of the mass loss. The production rate, mass escaping per unit time, increases as solar distance decreases, roughly following inverse square relationship with heliocentric distance for simple sublimation physics, though details depend on surface properties and thermal inertia. Early estimates suggest a few kilograms per second at discovery, perhaps increasing to tens of kilograms per second at perihelion. Not enormous by cometry standards, bright comets near the Sun can lose tons per second, but significant enough to create measurable non-gravitational acceleration, enough to shift the orbit by distances exceeding observational uncertainty. The molecules escape to space permanently. No mechanism exists to recapture them. No gravitational well deep enough to pull them back. No cold trap where they might recondense. They disperse into the solar system, adding infinitesimal contributions to the interplanetary medium, becoming part of the sparse gas that fills the space between planets. Eventually, solar wind sweeps them outward, or solar radiation ionizes them and magnetic fields accelerate them away. Within months or years, no trace remains of the volatiles that 3 Ice/Atlas loses during this passage. Only took 4.5 billion years for solar heating to drive sublimation from this particular ice deposit. Only took the object's trajectory to finally bring it close enough to a star for temperatures to exceed sublimation threshold. Only took the slow gravitational dance that launched it from its birth system, sent it drifting through the interstellar space, delivered it by chance into our sun's domain where photons could finally warm ice that might have remained frozen since stellar formation. Somewhere ahead in the object's trajectory lies perihelion, closest approach, where solar flux will peak and sublimation will reach maximum intensity. The date remains uncertain by days or weeks, depending on how strongly non-gravitational forces affect the orbit, how much thrust the outgassing produces, whether activity strengthens or weakens as different surface regions rotate into sunlight. Observers watch, measure, update their predictions. The object continues inbound, continues sublimating, continues responding to forces too gentle to name but strong enough to alter destiny across astronomical scales. Newton's third law requires every action to meet an equal and opposite reaction. Momentum conservation operating without exception across all scales from molecules to galaxies. When gas molecules leave a solid surface, ejected by thermal energy into surrounding space, the surface must recoil in the opposite direction. Individual molecules carry tiny momentum, mass measured in atomic units, velocity measured in hundreds of meters per second, but billions of molecules escaping per second accumulate to measurable thrust over time. The rocket equation, derived for engineered spacecraft, applies equally to comets outgassing in space. Thrust equals mass flow rate multiplied by exhaust velocity, force generated proportional to how much mass leaves and how fast it departs. For chemical rockets burning fuel in combustion chambers, exhaust velocities reach several kilometers per second, thrust measured in meganewtons, enough to lift payloads from Earth's surface against gravity. For sublimating ice releasing molecules at thermal speeds, exhaust velocities barely exceed half a kilometer per second, thrust measured in micronewtons or millinewtons, enough only to perturb orbits gently over months. 3 I/Atlas experiences this gentle perturbation continuously as it approaches the Sun. Active regions sublimating day and night if day and night have meaning for an object that rotates independent of solar synchronization. The thrust vector points roughly opposite to the local source of escaping gas, if molecules leave from the sunward side. The nucleus recoils away from the Sun. If molecules escape from other regions, rotation or surface heterogeneity creating different patterns. The thrust vector tilts accordingly, producing acceleration components radial, tangential, or normal to the orbit. The magnitude of acceleration depends on production rate and nucleus mass, neither known with precision in these early months after discovery. Production rate requires spectroscopic measurements, coma modeling, assumptions about gas expansion, velocity, and excitation efficiency. Nucleus mass requires estimating size from brightness and assuming bulk density, each assumption carrying factors of uncertainty that multiply through the calculation. Current estimates suggest accelerations around 10 to the minus 6 meters per second squared, a millionth of Earth's surface gravity. Imperceptible to human senses, but sustained over days and weeks. Accumulating velocity changes measured in meters per second, position changes measured in thousands of kilometers. The direction of acceleration remains uncertain without detailed surface imaging, without measurements of where activity concentrates, without models of how rotation modulates outgassing. Observations show the orbit deviating from pure gravitational predictions, residuals growing larger as the object approaches perihelion. But translating these residuals into specific thrust vectors requires sophisticated modeling. Orbital dynamics software that fits parameters to minimize position errors. Researchers construct these models iteratively. Start with pure gravitational prediction. Calculate where the object should appear based on Sun's mass and planetary perturbations. Compare prediction against observations. Measure residuals. Add non-gravitational parameters. Unknown coefficients representing thrust components in radial, tangential, and normal directions. Adjust coefficients until model predictions match observations within uncertainty limits. The process converges slowly, requiring weeks of data to constrain parameters adequately, requiring careful statistical analysis to avoid overfitting noise. The fitted parameters suggest predominantly radial acceleration, thrust pointing away from the Sun, consistent with sublimation from sunlit surfaces dominating the outgassing pattern. The radial component measures positive, meaning the object accelerates outward, slowing its infall slightly, extending the time required to reach perihelion. Tangential components appear smaller, less certain, possibly artifacts of insufficient data or possibly real effects from asymmetric activity. Normal components measure near zero within uncertainties, suggesting sublimation occurs roughly symmetrically about the orbit plane. These results match expectations for cometary behavior. Most active comets show similar patterns, radial acceleration dominating, magnitudes scaling with solar distance according to sublimation physics. The equations that describe 3I/Atlas's non-gravitational acceleration resemble equations developed for solar system comets. Same functional forms, similar parameter ranges. The physics respects no boundary between interstellar and solar system objects. Ices sublimate according to thermodynamics. Molecules carry momentum according to mechanics. Nuclei respond to thrust according to Newton's laws, regardless of origin. Yet, subtle differences might exist, details buried in the data noise, waiting for better measurements to resolve. The water production rate versus heliocentric distance might follow a different power law, reflecting different ice distribution or different thermal properties. The dust-to-gas ratio might differ from solar system averages, indicating different formation conditions in the interstellar medium. The non-gravitational acceleration might show time variability, suggesting active regions shutting down or new ones opening as sublimation erodes surface layers. The thrust, though tiny, proves sufficient to complicate trajectory prediction. Without accounting for non-gravitational forces, predictions of perihelion timing drift by hours or days. Position uncertainties grow to thousands of kilometers. Telescope pointing becomes unreliable for observations planned weeks in advance. Including non-gravitational terms improves predictions but introduces new parameters requiring estimation. Parameters that can only be determined by watching the object's behavior over extended periods, letting the accumulated observations constrain the model. The rocket effect operates continuously. No on-off cycles, no throttling, no control. Solar heating drives sublimation whenever illuminated surface temperatures exceed threshold values, producing thrust as long as volatile ices remain available at or near the surface. The process runs autonomously, determined by orbital geometry and rotation state and surface composition, variables beyond human influence, beyond measurement until after they manifest as observable effects. Combustion rockets achieve specific impulse, thrust per unit propellant mass, measured in hundreds of seconds. Efficiency limited by chemical energy release and nozzle design. Sublimation achieves lower specific impulse, molecules leaving at thermal velocities rather than combustion temperatures. No nozzle to focus flow. But sublimation requires no ignition, no pumps, no combustion chamber, operating reliably through thermal physics alone, continuing as long as ice and sunlight coexist on the same surface. The efficiency matters less than the inevitability. 3I/Atlas cannot choose to sublimate or not sublimate. Thermodynamics determines the outcome. At given temperature and pressure, ice either remains stable or transitions to vapor. Phase diagrams permitting no ambiguity. The object's trajectory changes because it must change, because momentum conservation allows no alternative when mass escapes asymmetrically. Only took 300 years from Newton's formulation of momentum conservation to spacecraft using reaction control systems for orbit adjustment. Only took another 50 years to develop models describing cometary non-gravitational forces. Recognizing that natural outgassing produces the same thrust effects that spacecraft achieve through deliberate venting, only took decades of observations tracking comets across multiple apparitions to measure these forces precisely, to validate models against data, to confirm that physics operates predictably across contexts, somewhere in the cold beyond Jupiter's orbit. 3I/Atlas continues accelerating under thrust measured in micronewtons, force too small to feel even if human hands could touch the surface, yet sufficient over weeks to alter velocity by meters per second, to shift arrival time at perihelion, to change the object's trajectory in ways that compound over the months remaining in its solar system passage. The molecules escape, momentum transfers, the nucleus responds. No drama attends the process. No visible change marks the moments when thrust accumulates to measurable velocity change. Just continuous operation of physical law. Momentum flowing from surface to space, one molecule at a time. Billions per second. Sustained across the slow fall toward perihelion. Photons carry momentum despite having no rest mass. A consequence of relativity's energy-momentum relationship, where even massless particles possess momentum proportional to their energy divided by light speed. Individual photon momentum measures infinitesimal. A single visible light photon carries momentum around 10 to the minus 27th kilogram meters per second, but sunlight delivers photons by the quadrillion per square meter per second. And at sufficient scales, even infinitesimal forces accumulate to measurable effects. Radiation pressure. The force exerted by light on surfaces it strikes, operates continuously throughout the solar system. Planets experience it, though their enormous mass renders the effect negligible compared to gravitational forces. Spacecraft feel it. Mission planners including radiation pressure in trajectory calculations for probes traveling to outer planets or escaping the solar system. Small particles experience it most strongly. Surface area to mass ratio favoring pressure effects, allowing photon momentum to compete with gravity. For dust grains lifted from 3I/Atlas during sublimation events, radiation pressure determines fate. Grains smaller than a micrometer experience forces that exceed solar gravity. Pushing them outward faster than gravity can pull them inward, accelerating them away from the nucleus and eventually out of the solar system entirely. Larger grains, millimeter-sized or bigger, experience weaker pressure relative to their mass, following trajectories only slightly perturbed from purely gravitational paths. Intermediate sizes occupy the regime where pressure and gravity balance delicately, creating complex orbital dynamics. The nucleus itself, measuring perhaps several hundred meters across, size uncertain, estimated only from brightness and assumed reflectivity, experiences radiation pressure weaker than sublimation, thrust, but not negligible over extended timescales. Photons striking the surface transfer momentum at rates proportional to solar flux and surface area, producing acceleration that points directly away from the Sun. Magnitude diminishing as inverse square of heliocentric distance. This acceleration resembles the Yarkovsky effect. Though technically distinct, Yarkovsky effect arises from thermal emission. Surfaces heated by sunlight re-radiate infrared photons. And since thermal emission peaks on the afternoon side of a rotating object, the momentum carried by emitted photons creates a thrust component. Radiation pressure is simpler, direct momentum transfer from incoming sunlight, no thermal lag involved, no dependence on rotation except insofar as rotation changes average surface area exposed to illumination. For 3I/Atlas, calculating radiation pressure requires knowing surface area and reflectivity. Observations suggest albedo around 10%, 90% of incident sunlight absorbed, 10% reflected. Dark surface, similar to carbonaceous asteroids, similar to other interstellar objects and long-period comets from the outer solar system. The darkness suggests organic-rich composition. Tholins or other carbon compounds coating the surface, materials that form readily in cold, radiation-exposed environments. The absorbed photons transfer their momentum twice, once when absorbed, again when re-emitted as thermal radiation. Perfect absorption and isotropic re-emission would produce net force equal to twice the momentum flux of incident sunlight. Real surfaces emit anisotropically, rotation and surface roughness and temperature gradients creating emission patterns that depend on geometry and thermal properties. But order of magnitude estimates still suggest radiation pressure acceleration around 10 to the -8 meters per second squared, 2 orders of magnitude weaker than sublimation thrust. Weak but persistent. Radiation pressure operates constantly as long as sunlight strikes the surface, requiring no volatile inventory, no sublimation threshold temperature, no active regions. The force continues even after sublimation ceases, even after the object recedes beyond distances where solar heating can drive ice transition. Unlike rocket thrust, which depletes with mass loss, radiation pressure sustains indefinitely. Solar photons arriving as long as the sun shines. The cumulative effect over months measures small but detectable. Position changes of hundreds of kilometers accumulate by the time 3I/Atlas passes perihelion, enough to shift predicted positions by amounts exceeding astrometric uncertainty. Orbital fitting software must include radiation pressure terms to achieve best fits. Parameters representing surface area and reflectivity entering the model alongside non-gravitational thrust components. Dust grains in the coma experience stronger relative pressure, their small size creating high area-to-mass ratios. Micron-sized grains accelerate at rates exceeding millimeters per second squared, reaching escape velocity from the nucleus within minutes of release, sweeping outward to form the dust tail that would appear prominently if 3I/Atlas were closer to the Sun and more active. At current distances and activity levels, the dust tail remains faint, barely extending beyond the coma. Particles dispersing gradually rather than forming a dramatic streamer. The grain size distribution affects tail morphology and brightness. Small grains scatter light efficiently but get pushed away quickly by radiation pressure. Large grains remain near the nucleus longer but scatter light weakly, contributing less to observed brightness. Intermediate sizes optimize visibility, balancing scattering efficiency against residence time in observable regions near the nucleus. Observers analyzing tail structure can infer grain size distributions, working backward from brightness patterns to estimate what size particles dominate the dust production. For 3I/Atlas, the dust appears subordinate to gas. Dust-to-gas ratio estimated below unity, meaning more mass escapes as vapor than as solid particles. This ratio suggests either friable, ice-rich composition or gentle sublimation regime where gas escapes without entraining much dust, different from some solar system comets that produce dust-rich comas, particles dominating over gas, creating dramatic tails visible to naked eye even from Earth. The photons themselves, traveling from sun to object, carry no information about their destination, no targeting, no awareness. They simply propagate electromagnetic oscillations in vacuum, spreading outward from the solar surface at 300,000 kilometers per second, intensity diminishing as inverse square of distance. Some photons strike 3I/Atlas, transfer momentum, scatter or absorb. Most photons miss, continuing outward indefinitely, spreading through the solar system and eventually into interstellar space, carrying energy and momentum that will never interact with anything, propagating until universe ends or until improbable collision with distant matter. Only took Maxwell's equations and Einstein's relativity to predict radiation pressure from first principles. Only took careful experiments in early 20th century to measure the effect directly, confirming theoretical predictions, demonstrating that light indeed pushes on surfaces. Only took spacecraft era to make radiation pressure practically relevant, mission planners calculating trajectory perturbations, solar sail designers proposing propulsion systems based entirely on photon momentum. Somewhere in the space around 3I/Atlas, dust grains drift outward under radiation pressure, accelerating slowly away from the nucleus, some escaping the coma entirely, others falling back under weak gravity, all responding to the constant photon rain that bathes the inner solar system. The nucleus itself experiences pressure, feels the gentle push of starlight, velocity changing by micrometers per second, position shifting by centimeters per hour, trajectory bending imperceptibly but persistently under forces that require no fuel. No mechanism beyond electromagnetic waves carrying momentum through vacuum. Telescopes track 3I/Atlas night after night, measuring position against background star fields, recording right ascension and declination to fractions of an arcsecond. Each measurement captures the object's location at a specific moment in universal time, a data point encoding where photons from the object converged on detector pixels after traversing interplanetary space at light speed. These positions accumulate in databases, tables growing longer with each observation session, each entry time-stamped and annotated with observatory code, telescope specifications, measurement uncertainty estimates. Astrometry, the precise measurement of celestial positions, requires careful calibration against reference stars whose coordinates are known to milliarc-second precision from space-based surveys. The reference frame matters, positions measured relative to stars that themselves move through the galaxy, proper motions accumulating over years, requiring corrections to maintain consistent coordinate system. Software handles these corrections automatically, querying stellar catalogs, applying parallax and proper motion adjustments, transforming raw pixel coordinates into standardized celestial positions. The precision achievable depends on telescope aperture, seeing conditions, exposure time, detector quality. Large professional observatories achieve astrometric precision below 100 milliarc seconds under good conditions, enough to measure positions of faint objects like 3I/Atlas with uncertainties smaller than the object's own coma diameter. Smaller telescopes contribute data with larger uncertainties, but still valuable for constraining orbits, especially when observations span weeks or months. Baseline extending position arc. For 3I/Atlas, observations arrive from dozens of facilities across continents and hemispheres. Some observatories contribute single nights of data, brief participation when telescope schedules permit. Others track the object repeatedly. Dedicated follow-up programs acquiring positions every few nights, building dense time series that capture short-term variations and long-term trends. All data funnels to central clearinghouses, the Minor Planet Center, and similar organizations that aggregate observations, perform preliminary orbit calculations, distribute results to interested researchers. The residuals, differences between observed positions and positions predicted by gravitational orbit models, show systematic patterns, not random scatter around zero, but persistent offsets that grow with time, indicating the model misses some component of the object's motion. Plotting residuals versus time reveals structure. Maybe sinusoidal variations suggesting rotation-modulated effects. Maybe monotonic drift indicating sustained acceleration in one direction. These patterns signal non-gravitational forces operating as predicted. Pure gravitational models assume the object responds only to Sun's inverse square attraction and planetary perturbations, forces calculable exactly from known masses and positions. But 3I/Atlas deviates from gravitational prediction. Observed positions lagging or leading expected positions by amounts that exceed measurement uncertainty. The deviations confirm active outgassing, confirm that sublimation thrust perturbs the trajectory measurably. Fitting improved models requires adding non-gravitational parameters to the orbit determination software. Standard approach includes 3 parameters, A1, A2, A3, representing acceleration components in radial, tangential, and normal directions. Radial component A, 1 points away from Sun, positive values indicating outward push. Tangential component A2 lies in the orbit plane perpendicular to radial, positive values accelerating the object along its motion. Normal component A 3 points perpendicular to orbit plane, positive values pushing northward by convention. The software adjusts these parameters iteratively, minimizing sum of squared residuals across all observations, finding parameter values that best reproduce observed positions. The process resembles curve fitting but operates in celestial mechanics space, each parameter change altering predicted orbit subtly. Software exploring parameter space, searching for optimal solution. Convergence requires sufficient observations spanning adequate time baseline. Too few data points and parameters remain poorly constrained. Uncertainties large. Multiple solutions fitting equally well. For 3I/Atlas, months of observations gradually constrain the parameters. Early fits show large uncertainties, parameters uncertain by factors of 2 or 3. Multiple models fitting data adequately. Later fits tighten, uncertainties shrinking as more observations accumulate, as baseline extends, as the object's deviant behavior becomes unmistakable. The radial component A1 emerges strongest, magnitude around 10 to the -6 meters per second squared, consistent with sublimation thrust pushing outward. Tangential and normal components measure smaller, perhaps real or perhaps noise, requiring more data to confirm. Each observatory contributing data increases confidence in the orbital solution. Independent measurements from different telescopes, different hemispheres, different instrumental systematics, all converging on consistent position measurements, arguing against systematic errors or calibration problems. If one telescope showed consistent offset, that might indicate instrument issues. When dozens of telescopes agree within quoted uncertainties, confidence increases that measurements reflect reality rather than artifacts. The observation strategy evolves as the object's trajectory becomes clearer. Early on, observers simply acquire whatever data they can whenever possible, building up position arc, establishing that the orbit is hyperbolic, confirming interstellar origin. Later, as non-gravitational effects become apparent, observation planning prioritizes times when those effects should show most clearly, near perihelion when outgassing peaks, or during specific rotation phases if rotation period can be determined. Some observers specialize in photometry rather than astrometry, measuring brightness changes rather than positions, seeking rotation signatures or activity variations. These measurements complement astrometry, providing context for interpreting orbital deviations. If brightness varies with rotation period and astrometric residuals show similar periodicity, that suggests rotation-modulated outgassing creating time-varying thrust, evidence linking physical properties to dynamical behavior. Tracking astrometric residuals across months resembles detective work, piecing together clues from scattered observations, inferring physical processes from mathematical patterns. The object itself moves silently through space, unaware of telescopes measuring its position, unconcerned with software fitting parameters to minimize residuals. The residuals exist only in human analysis. Differences between model and measurement, discrepancies that reveal where understanding remains incomplete, only took 4 centuries from Tycho Brahe's naked-eye astrometry achieving arc-minute precision to modern space-based observatories achieving milliarc-second precision, improvement by factor of 100,000. Only took development of CCD detectors, automated telescopes, sophisticated calibration algorithms, international cooperation to make precise astrometry routine rather than heroic. Only took recognition that small deviations from predicted positions carry information, that residuals are not merely errors but signals waiting for interpretation, somewhere in the data tables growing in astronomical databases. The positions of 3 I/Atlas accumulate, right ascension and declination paired with observation times, uncertainties attached, observatory codes noted. Each entry represents photons captured, light that began as solar radiation reflecting from distant ice, traveling millions of kilometers to focus on detector pixels, converting to electronic signals, processing through calibration pipelines, emerging as celestial coordinates precise to fractions of an arcsecond. The positions tell a story of motion perturbed, trajectory altered by forces too subtle to see directly, but strong enough to measure through patient accumulation of observations across weeks and months. The coma surrounding 3 I/Atlas extends asymmetrically, gas and dust distributed unevenly around the nucleus, brightness varying with direction from the central condensation. Images show enhancement sunward, where fresh molecules escape into illumination, and extension tailward, where radiation pressure and solar wind push released material away from the sun. The geometry creates a teardrop shape, blunt on the sunward side, tapering into a faint tail stretching anti-sunward. Morphology familiar from countless comets observed through centuries of patient watching. This asymmetry matters for understanding non-gravitational forces because thrust direction depends on where mass escapes. If gas molecules leave preferentially from the sunward hemisphere, sublimation driven by direct solar heating, the nucleus recoils anti-sunward, producing acceleration opposite the sun. If molecules escape from other regions, the terminator where day transitions to night, or the anti-solar hemisphere warmed by thermal conduction through the nucleus interior, thrust vectors tilt, creating components tangential or even partially sunward. The brightness distribution maps the gas density distribution, at least approximately. More molecules per cubic meter scattering more sunlight, creating brighter regions in the coma. Photometry measures brightness as function of position angle and distance from nucleus, producing radial profiles and azimuthal scans that reveal structure. For 3I/Atlas, these measurements show the expected sunward enhancement. Brightest region offset slightly toward the sun, consistent with active sublimation on the day side. But the offset measures small, just a few degrees from the sun-comet line, suggesting either nearly symmetric activity or viewing geometry that obscures stronger asymmetries. The viewing geometry matters. Earth-based observations see projected coma. Three-dimensional structure collapsed onto two-dimensional sky plane. Foreshortening and projection effects changing apparent shapes depending on viewing angle. True three-dimensional structure requires modeling, requires assumptions about how gas expands from the nucleus, how density decreases with distance. Modeling coma morphology starts with assumptions about source geometry. Simplest model assumes isotropic emission, molecules leaving nucleus uniformly in all directions, density decreasing as inverse square of distance from source. This model predicts symmetric round coma, brightness depending only on radius from nucleus, no directional variations. Observations immediately rule this out. The coma shows clear asymmetry. Clear enhancement toward the sun. Next sophistication adds directional preference. Perhaps cosine law emission, where outgassing rate varies as cosine of angle from surface normal, mimicking how solar heating varies across a rotating sphere. This produces sunward enhancement, but still assumes all surface regions contribute equally when illuminated. Real nuclei show heterogeneity. Active regions concentrated in specific areas. Inactive regions contributing little outgassing. Activity modulated by rotation as different faces turn toward the sun. For 3I/Atlas, the rotation period remains uncertain. Light curves showing variations, but periodicity unclear, may be buried in noise or maybe not strictly periodic if the nucleus tumbles chaotically rather than spinning around a stable axis. Without knowing rotation period, predicting how activity patterns evolve over hours becomes difficult. Models unable to account for time-varying source geometry. Dust adds complexity. Gas molecules expand at thermal velocities, hundreds of meters per second, escaping the nucleus gravity easily, reaching distances of thousands of kilometers within hours. Dust particles move slower, radiation pressure accelerating them gradually. Larger grains barely reaching escape velocity, creating stratification where grain size correlates with distance from nucleus. The dust scatters sunlight more efficiently than gas, contributing disproportionately to brightness despite representing less total mass, affecting observed coma morphology in ways that complicate interpretation. The dust-to-gas ratio estimated from spectroscopy and brightness measurements suggests dust comprises maybe 20% of ejected mass, rest being water vapor and other gases. This ratio affects how coma brightness relates to production rate, affects how much thrust the outgassing produces per unit brightness, affects predictions for how activity will evolve as solar distance changes. High dust-to-gas ratios mean more mass loss per photon scattered, stronger thrust for given brightness. Low ratios mean gas dominates mass loss, brightness mostly from dust, while thrust mostly from invisible vapor. The tail, extending anti-sunward from the coma, measures faint and short in 3I/Atlas images, barely distinguishable from background sky except in deep exposures with careful image processing. Bright comets close to the sun produce tails millions of kilometers long, visible to unaided eye. Dramatic streamers curving across the sky as orbital motion and solar wind influence tail geometry. At 3I/Atlas's current distance and activity level, the tail extends perhaps 10,000 kilometers, modest structure requiring patient imaging to detect. Tail morphology encodes information about dust grain properties and radiation pressure. Dust tails curve slightly, particles following individual orbits after leaving the nucleus, radiation pressure pushing them anti-sunward, while gravity pulls them along orbital path, resulting in curved trajectory that lags behind the nucleus. The curvature depends on grain size. Small grains pushed harder by radiation pressure curve more strongly, large grains curve less. Spectrum of sizes producing spread in tail geometry. Gas tails, ionized by solar ultraviolet and swept by solar wind magnetic fields. Point more directly away from sun. Less curved than dust tails, sometimes showing structure from magnetic field interactions. For 3I/Atlas, the gas tail remains invisible in most observations, too faint to detect above background, requiring specialized imaging techniques or space-based ultraviolet observations to reveal. The dust tail dominates what little tail structure appears in visible light images. Comparing coma morphology across observations separated by days or weeks reveals evolution, changes suggesting rotation bringing new regions into sunlight, or depletion of active areas as sublimation erodes volatile deposits, or development of new active regions as overlying dust mantle breaks apart. These changes complicate modeling, but offer insights into surface properties, into how ice distribution varies across the nucleus, into processes that control where and when sublimation occurs. The geometry dictates momentum, transfer efficiency. Molecules leaving the sunward hemisphere push the nucleus anti-sunward, creating acceleration that slows infall, extends time to perihelion. Molecules leaving the trailing hemisphere push forward along the orbit, accelerating the nucleus in its motion, shortening orbital periods slightly. Molecules leaving in other directions create thrust components that tilt the orbital plane or change eccentricity. Observing which directions dominate requires measuring astrometric residuals carefully, fitting models to distinguish between different acceleration geometries. Only took decades of comet observations to recognize that coma asymmetry correlates with non-gravitational acceleration, that bright regions indicate active areas, that morphology changes provide clues about rotation and surface heterogeneity. Only took development of numerical models tracking gas expansion and dust dynamics to interpret observations quantitatively, to extract physical parameters from brightness distributions. Only took recognition that every visible feature in a coma corresponds to invisible momentum transfer, photons revealing processes that alter trajectories. Somewhere around 3I/Atlas, molecules expand outward from the nucleus in patterns determined by surface temperature and ice distribution and rotation state, scattering sunlight in proportions that create the teardrop-shaped coma visible in telescope images. The pattern encodes information waiting for interpretation, brightness variations mapping source regions, morphology changes revealing rotation and evolution, structure, documenting the quiet transfer of momentum from nucleus to coma as volatile inventory depletes one molecule at a time across the slow months of solar system passage. Rotation adds another dimension to the dynamics, the nucleus spinning around some axis at some rate measured in rotations per day or hours per rotation. Orientation in space determining which hemisphere faces sunward at any moment. This rotation modulates outgassing, active regions moving into and out of sunlight, sublimation rates varying with local solar time, creating time-dependent thrust that depends not just on heliocentric distance, but on rotation phase and surface geography. The torque produced by outgassing operates through the same momentum conservation that creates translational thrust. If molecules escape symmetrically from the rotation axis, no net torque results. Angular momentum remains constant, but asymmetric outgassing jets from specific latitudes. Active regions offset from the rotation pole. Preferential sublimation on one hemisphere creates torque, changes rotation rate, alters spin axis orientation over time. For most comets, these torques remain small compared to rotational angular momentum, changing spin periods by seconds or minutes over an apparition, detectable only through careful monitoring across months. But sustained torque acting over many orbits can produce significant evolution, rotation periods speeding up or slowing down, spin axes precessing through space, tumbling states replacing stable spins. 3. I/Atlas shows no obvious rotational signature in early light curve observations. Brightness variations suggesting possible periodicity around 10 hours, but with low amplitude and significant scatter. This might mean the nucleus is nearly spherical. No large-scale asymmetry to create brightness variations as it rotates. Or it might mean the rotation axis points nearly toward Earth. Pole-on view showing little brightness change as the nucleus spins, or the nucleus might tumble chaotically. No stable rotation period. Brightness variations irregular and unpredictable. Determining rotation period precisely requires photometry spanning multiple rotation cycles, preferably from multiple observatories to provide continuous coverage without gaps from daylight or weather. Each observation measures brightness at specific time. Plotting brightness versus time reveals periodic patterns if they exist. Fourier analysis or period-finding algorithms extracting dominant frequencies from the data. For 3 I/Atlas, the available photometry shows hints but not proof. Suggested period around 10 hours, appearing in some analyses but failing significance tests in others, possibly real or possibly artifact of observing cadence or data gaps. More observations are needed, continuous monitoring over several days, sufficient coverage to distinguish rotation signal from noise and from secular brightness changes as activity evolves. The torque magnitude depends on where active regions locate relative to rotation axis and center of mass. Active regions at the equator produce maximum torque for given mass loss rate, leveraging rotation radius to create angular momentum transfer. Active regions near the poles produce less torque, smaller moment arm reducing rotational effect even though translational thrust remains similar. If outgassing occurs preferentially on the afternoon side of the nucleus, thermal lag causing maximum sublimation to occur hours after peak solar heating, the torque acts to spin up the rotation, days getting shorter over time. This happens because molecules leaving the afternoon hemisphere carry prograde angular momentum, conservation requiring the nucleus to acquire retrograde angular momentum, spinning faster to compensate. The effect resembles YORP, Yarkovsky-O'Keefe-Radzevsky-Paddock, effect but driven by sublimation rather than thermal re-radiation. Conversely, if outgassing peaks on the morning side may be due to different ice distribution or subsurface thermal properties, torque acts to slow rotation, spin period increasing over time. The direction and magnitude of evolution depends on details that remain unknown without better rotation determination and surface mapping. The spin axis orientation matters for understanding how activity varies with heliocentric distance. If the pole points perpendicular to the orbit plane, the nucleus experiences seasonal variations, one hemisphere staying sunlit for months while the other remains dark. Sublimation concentrated in one hemisphere, creating sustained thrust in specific directions. If the pole lies in the orbit plane, the nucleus experiences equal illumination in both hemispheres averaged over rotation. Sublimation more symmetric, thrust patterns different. For 3 I/Atlas, the pole orientation remains unknown. No measurements constraining spin axis direction. Modeling unable to determine whether seasonal or diurnal patterns dominate the activity. The hyperbolic trajectory means the object passes through the solar system only once. No seasonal cycles repeating. No opportunity to observe multiple apparitions and watch rotation evolution across orbits. tumbling complicates everything. Instead of spinning around a stable axis, a tumbling nucleus rotates chaotically, orientation changing unpredictably. Brightness variations irregular. Torque effects difficult to calculate. Tumbling can arise from asymmetric mass loss, outgassing torques exciting wobble, driving rotation away from stable principal axis spin, or tumbling might result from collisions or tidal encounters in the object's history, setting it spinning in complex fashion that persists for ages. Detecting tumbling requires dense photometric coverage revealing irregular patterns, maybe multiple periodicities corresponding to rotation around different axes, maybe chaotic variations that resist period-finding algorithms. For 3I/Atlas, the current data cannot distinguish between stable, low-amplitude rotation and chaotic tumbling, insufficient signal-to-noise and coverage gaps preventing definitive conclusion. The rotation state affects how astrometric residuals behave. Stable rotation with fixed pole orientation produces regular patterns. Non-gravitational acceleration varying sinusoidally as active regions rotate in and out of sunlight. Tumbling produces irregular patterns. Acceleration direction changing unpredictably, making orbital fitting more difficult, requiring more complex models with additional parameters. Only took centuries of observing rotating bodies, planets, moons, asteroids, to develop techniques for measuring rotation periods and pole orientations from light curves. Only took decades of spacecraft missions to reveal surface features creating rotation variations, active regions and albedo patterns explaining why brightness changes with viewing geometry. Only took recognition that rotation couples to orbital dynamics through torque, that spin states evolve, that what rotates today may rotate differently tomorrow, somewhere in space. 3I/Atlas spins or tumbles at a rate unknown, axis orientation unknown, surface features creating brightness patterns too subtle yet to measure confidently. The rotation continues independent of observation. Momentum conserved, angular velocity changing only when torques act, evolution proceeding according to physics whether humans watch or not. The torque from outgassing, if it operates, changes spin infinitesimally each day, fractions of a degree per rotation, accumulating over months toward effects that might become measurable before the object recedes beyond detection limit, or might remain buried in noise. Another mystery unsolved because observations ended before patterns became clear. Thermal physics introduces lag between solar heating and surface response, rock and ice requiring time to warm. Thermal energy propagating through material at rates determined by conductivity and heat capacity, creating delays between peak illumination and peak temperature. This lag matters because sublimation rate depends exponentially on temperature. Small temperature changes producing large changes in vapor pressure, shifting maximum outgassing away from the subsolar point toward the afternoon side of rotating bodies. The afternoon effect, well documented for asteroids experiencing Yorp torques, applies equally to sublimating comets, though the mechanism differs. Asteroids re-radiate absorbed sunlight as thermal infrared. Afternoon surfaces emitting more energetically than morning surfaces still warming from night cold. Comets sublimate volatiles. Afternoon surfaces releasing more molecules as they reach peak temperature hours after local noon. Both phenomena arise from thermal inertia, material resistance to rapid temperature change. For 3I/Atlas, the thermal properties remain uncertain. No measurements of surface conductivity or heat capacity. Models forced to assume values based on other comets or laboratory studies of ice dust mixtures. Typical assumptions suggest thermal skin depths of centimeters to meters, meaning solar heating affects only shallow surface layers, deeper interior remaining cold and insulated. The skin depth determines how quickly surfaces respond to changing illumination, how much thermal memory persists from previous rotation cycles. Thermal modeling requires solving heat diffusion equations, tracking how energy deposited by absorbed sunlight propagates into the interior, how temperature varies with depth and time, how sublimation removes energy through latent heat of vaporization. The equations couple thermodynamics and mass transfer. Sublimation cooling the surface, heat conduction bringing energy from below or from adjacent regions, solar radiation adding energy where it strikes directly. The models predict peak surface temperature occurring several hours after local noon for rotation periods around 10 hours and thermal inertia values typical of cometary material. This offset means maximum sublimation happens on the afternoon hemisphere, molecules escaping preferentially from regions that have had time to warm, creating thrust that lags solar direction by tens of degrees. The lag angle depends on thermal inertia and rotation period. Faster rotation, allowing less time for heat to diffuse, creating larger lag angles. This temporal offset produces thrust components that accelerate or decelerate the nucleus along its orbit. Unlike purely radial thrust that only changes speed of approach or recession from the Sun, afternoon side sublimation from a prograde rotating nucleus pushes backward relative to orbital motion, slowing the object slightly, creating drag-like effect though the mechanism involves no atmosphere or friction. The magnitude depends on how strongly sublimation concentrates in the afternoon sector and how much total mass escapes. For 3I/Atlas, measuring these subtle effects requires precise astrometry over months, watching for specific patterns in residuals that indicate tangential acceleration components. Early orbital fits suggest possible tangential component, but with large uncertainties. Insufficient data to confirm or rule out afternoon effect torques. More observations accumulating through perihelion passage should constrain these parameters better, allowing models to distinguish between symmetric and asymmetric outgassing patterns. The lag affects how much momentum transfers per molecule escaping. Molecules leaving the subsolar point push directly anti-sunward, creating purely radial acceleration. Molecules leaving the afternoon terminator push at angle. Components anti-sunward and backward along orbit. Total thrust vector tilted from radial direction. The tilt angle matches the thermal lag angle approximately. Geometric relationship between where heating occurs and where maximum sublimation responds. Subsurface ice complicates the picture. If dust layers cover ice deposits, heat must conduct through dust before reaching volatile material. Additional thermal lag accumulating from surface to sublimation front. The escaping gas must diffuse through porous overburden. Pressure gradients driving flow. Molecules following tortuous paths before reaching space. These processes add delays. Shift timing of gas release further from solar heating patterns, creating phase lags larger than simple surface thermal inertia would predict. Some models suggest subsurface sublimation might occur meters below the surface, solar heat penetrating through insulating dust over days or weeks, driving gas production from depths where seasonal rather than diurnal cycles dominate, for long-period comets making rare trips through the inner solar system. These deep reservoirs might contain pristine ice unmodified by previous outgassing, preserving volatiles from formation epoch billions of years ago. 3I/Atlas, making its first and only passage near a star, might show different thermal behavior than solar system comets that have approached the Sun repeatedly. Fresh, unweathered surface. No dust mantle built up from previous activity. Ice exposed directly to space in some regions, while buried under primordial regolith in others. The thermal response depends on these unknowns. Surface properties that can only be inferred indirectly from observed activity patterns. The thermal wave propagating into the nucleus during approach continues propagating outward during recession. Stored heat gradually conducting back to surface, potentially sustaining sublimation even as solar flux decreases. This hysteresis means activity need not track solar distance symmetrically. Outgassing during outbound leg possibly exceeding inbound levels at equivalent distances. Thermal memory, maintaining elevated temperatures for weeks or months. Observations of solar system comets confirm this behavior, many showing brighter comas post-perihelion than pre-perihelion at the same heliocentric distance, asymmetry attributed to thermal lag and to changes in active area as sublimation erodes different surface regions. For 3 I/Atlas. Watching for similar asymmetry requires observations spanning perihelion and continuing months afterward, comparing activity levels at matched solar distances on approach and recession. The energy balance determines how much ice can sublimate. Solar flux delivers power measured in watts per square meter, absorbed radiation heating the surface, some energy conducting inward, some re-radiating as thermal infrared, remainder consuming in sublimating ice. Latent heat of vaporization drawing roughly 300 kilojoules per kilogram for water ice. The fraction going to sublimation depends on surface temperature. Thermal properties, how efficiently heat reaches ice deposits. Efficiency appears low for many comets, perhaps only a few % of absorbed solar energy actually driving sublimation. Rest conducting away or re-radiating before it can vaporize ice. This inefficiency means production rates remain modest even when solar flux seems substantial. Thermal losses limiting how fast volatiles can escape, creating ceiling on outgassing intensity independent of ice availability. For 3 I/Atlas at current distances, solar flux measures around 50 watts per square meter. Order of magnitude estimate for how much power sunlight delivers to each square meter of surface. If even 10% goes to sublimation, that provides 5 watts per square meter, enough to vaporize roughly 50 milligrams of water ice per second per square meter. Multiplying by active surface area, perhaps a few square kilometers if much of the nucleus remains inactive, yields total production rates of kilograms per second, consistent with spectroscopic estimates and coma brightness observations. The calculation remains approximate. Uncertainties compounding at each step. But order of magnitude agreement between energy budget and observed activity suggests the basic physics captures what happens. Sunlight warms surface. Heat drives sublimation. Vapor escapes carrying away energy and momentum. Surface cools from vaporization. Equilibrium establishes where heat input balances. Heat losses, including sublimation cooling, only took thermodynamics and heat transfer theory developed over centuries to predict how surfaces respond to solar heating. Only took recognition that phase transitions require energy, that sublimation consumes heat, that thermal properties determine response timescales. Only took application of these principles to rotating bodies in space, accounting for variable illumination and vacuum boundary conditions and coupling between temperature and outgassing rate. Somewhere on 3 I/Atlas's surface, afternoon regions reach peak temperature hours after the sun transited local meridian. Thermal energy accumulated during morning hours, finally raising surface above thresholds where sublimation accelerates. Molecules escaping at rates proportional to vapor pressure, increasing exponentially with temperature. The molecules leave, carrying momentum. The surface recoils. Thrust vectors pointing at angles determined by thermal lag and rotation geometry. The lag persists, predictable consequence of thermal inertia. Planetary memory operating at scales of hours and meters, connecting past heating to present outgassing in patterns invisible to observers, but encoded in astrometric residuals waiting for sufficiently precise measurements to reveal. The catalogue of interstellar visitors, though sparse with only 3 confirmed members, by the time 3 I/Atlas receives designation, permits comparison across the sample. Seeking patterns or highlighting differences that might reveal the diversity of objects ejected from other planetary systems. Each visitor carries information about its origin system, about formation conditions and dynamical history, information encoded in composition. Structure, activity level, trajectory through our solar system. 1. Oumuamua arrive first in observational history, though not necessarily first in actual passage through the inner system. Detection bias favors recent arrivals. Past visitors likely passed unnoticed before survey capabilities improved. Its discovery in October 2017 startled astronomers. Hyperbolic orbit immediately apparent. Motion too fast for solar system membership. The object appeared elongated. Light curve variations suggesting axis ratio around 10. 1. Cigar-shaped or possibly flat, like a pancake. Geometry unusual for natural bodies, though uncertainties remained large. Most puzzling. Oumuamua showed non-gravitational acceleration despite lacking visible coma. No dust tail, no spectroscopic evidence of outgassing. The acceleration measured small but significant, changing trajectory measurably, requiring explanation beyond pure gravity. Proposed mechanisms range from conventional outgassing, too weak to produce visible coma, to exotic hypotheses involving radiation pressure on thin shapes, to speculation about artificial origin that most astronomers dismissed as unlikely. The debate continues years later, available data insufficient to determine composition definitively. The object having departed the inner solar system before detailed characterization could occur. What observations exist suggest neutral color, maybe slight reddening, albedo uncertain, mass unknown, density unconstrained. The name, meaning scout or messenger from afar arriving first in Hawaiian, acknowledges both its discovery location and its status as the first recognized interstellar visitor. 2I/Borisov followed in August 2019, discovered by amateur astronomer Gennady Borisov, who spotted the faint fuzzy object moving unusually fast through his telescope images. This object behaved conventionally, showing obvious coma from first detection, brightening as it approached the sun, spectrum revealing water vapor, carbon monoxide, other typical cometary volatiles. The activity matched solar system comets well, suggesting familiar composition. Similar formation processes despite originating around different star. Borisov's non-gravitational acceleration followed expected patterns, radial component dominating, magnitude consistent with observed gas production rates, no mysteries requiring exotic explanations. The nucleus appeared somewhat redder than typical solar system comets, color measurements suggesting surface enriched in organics, but not dramatically different, well within the range solar system diversity spans. The object reached perihelion at 2 astronomical units from the Sun, inside Mars' orbit but outside Earth's, approaching close enough for detailed spectroscopy. Photometry. Coma imaging. Observations detected CO at unusually high abundance relative to water compared to typical solar system comets, suggesting formation in colder environment or different chemical pathways. The dust appeared depleted in certain elements, compositional differences hinting at different nebula chemistry in the formation region. Now 3I/Atlas joins this small catalog, neither as enigmatic as Oumuamua nor as conventional as 2I/Borisov. Occupying intermediate position, it shows coma, confirming volatiles present and active, ruling out purely rocky or metallic composition. It undergoes non-gravitational acceleration consistent with outgassing, behavior explainable through standard cometary physics, but it remains fainter than Borisov at comparable distances, either smaller nucleus or lower activity level or higher dust-to-gas ratio affecting brightness efficiency. Composition appears similar to solar system comets based on preliminary spectroscopy, water ice, carbon dioxide, possible organics. Nothing obviously alien or exotic in the chemical inventory. This consistency across the interstellar sample, all 3 objects showing either inactive surfaces or conventional cometary volatiles, suggests planet formation produces similar outcomes in different stellar systems, at least for objects massive enough to reach interstellar space. The ejection mechanisms that launch objects from their birth systems into interstellar trajectories remain theoretically understood but observationally unconstrained, gravitational scattering by giant planets can accelerate smaller bodies to escape velocity. Similar to how Jupiter occasionally ejects comets from the solar system, close stellar encounters might strip outer regions of planetary systems, liberating objects into the galaxy. Supernovae or other catastrophic events could eject material, though probably destroying most objects through intense radiation or shock heating. Whatever mechanisms operate, they apparently function commonly enough that interstellar visitors pass through the inner solar system regularly. Statistical estimates based on the detection rate and survey completeness suggest perhaps one object within Jupiter's orbit per year, scaling to many more at larger distances. The solar system swimming through a sparse sea of wandering debris from countless planetary systems across the galaxy's history, the three confirmed objects span different size ranges if brightness reflects size appropriately. Oumuamua measured perhaps 100 meters in longest dimension, smaller than typical comets, but large enough to survive interstellar journey without catastrophic erosion. Borisov appeared larger, maybe kilometer-scale nucleus, more massive and brighter. 3I/Atlas falls between, several hundred-meter scale estimated from brightness. Though albedo uncertainty makes size estimates provisional, their trajectories through the solar system differ in geometry and velocity. Oumuamua passed swiftly, high hyperbolic excess velocity, weeks from discovery to departure beyond observation range. Borisov lingered longer, slower passage allowing months of observation, perihelion within inner solar system providing close approach for detailed study. 3I/Atlas follows intermediate path, observable for months but not approaching as close as Borisov, speed sufficient to escape but not dramatically fast. The sample of 3 permits no robust statistics, no confident statements about typical properties or standard behaviors. Each object represents individual case, possibly representative of some population or possibly outlier, impossible to determine from 3 examples. Astronomers await 4Y/5I subsequent discoveries that will gradually build population statistics, reveal frequency distributions of properties, constrain theoretical models of interstellar object populations. Comparison highlights what remains unknown. All 3 objects discovered by automated surveys or dedicated amateurs, none found incidentally by observers searching for other targets, suggesting many fainter objects pass undetected. All 3 discovered after entering inner solar system. Inbound trajectories providing increasing brightness. No confirmed detections of outbound objects fading beyond detection threshold. This observational bias favors bright, active, approaching objects, leaving population of dark, inactive, or receding visitors largely invisible. The detection rate continues improving as survey capabilities expand. Larger telescopes, more sensitive detectors, better software detecting motion against star fields, cadence increasing to capture fainter objects moving faster. Future facilities like the Vera Rubin Observatory promise detection rates potentially 10 times higher. Finding interstellar visitors routinely. Building the statistical sample that will transform these rare curiosities into characterized population. Only took 2 centuries from first comet orbit calculations to recognition that hyperbolic orbits indicate interstellar origin. Only took decades more to develop technology capable of detecting such objects reliably. Distinguishing them from abundant solar system population. Only took 3 confirmed detections to establish nomenclature, analysis techniques, observational protocols that will serve for future discoveries. Somewhere in the archive of known interstellar objects, 3I/Atlas occupies its position between Oumuamua's mystery and Borisov's familiarity, data accumulating, characteristics emerging, comparison revealing both commonalities and differences among visitors from beyond. The catalog grows slowly. 1 entry per year or 2, each addition refining understanding incrementally, each object contributing unique details while fitting into emerging patterns. The collection documenting that the galaxy contains wandering debris from planetary formation, objects that condensed around other stars, orbited briefly or never in their native systems, escaped through dynamics or catastrophe to coast through interstellar space until chance brought them near our Sun, where humans evolved barely in time to notice their passage. The orbital solution improves gradually as observations accumulate month after month, each new position measurement constraining parameters more tightly, uncertainties shrinking as baseline extends and as the object's deviant behavior relative to pure gravitational prediction becomes unmistakable. Software iterates continuously, incorporating new data as observatories report positions, refitting parameters, updating predictions for where the object will appear in coming nights. The process resembles focus adjustment. Initial images blurry, details unclear, successive refinements sharpening understanding until features emerge with clarity. Early orbital solutions carried large uncertainties. Perihelion distance uncertain by millions of kilometers, perihelion timing uncertain by weeks, non-gravitational parameters barely constrained, multiple models fitting data equally well. Later solutions converge, parameters stabilizing, predictions becoming reliable enough for planning observations months in advance. The non-gravitational parameters receive particular attention as the data set matures. The radial component A1, representing thrust away from the Sun, emerges strongest and most certain. Value settling around 8 times 10 to the minus 7 meters per second, squared with uncertainties shrinking to 20%. This magnitude implies gas production rates of several kilograms per second at current distances, reasonable for a comet of this size and activity level, consistent with coma brightness and spectroscopic detections. The tangential component, A2 representing acceleration along the orbital path, shows smaller magnitude with larger relative uncertainty, maybe real or maybe statistical fluctuation, requiring more data to determine confidently. Positive values would indicate forward acceleration, possibly from afternoon-side outgassing on a prograde rotating nucleus. Negative values would indicate backward push, drag-like effect slowing orbital motion. Current best fit value hovers near zero within error bars, suggesting either symmetric outgassing or insufficient sensitivity to detect the subtle tangential effects. The normal component A3, perpendicular to orbit plane, measures near zero consistently across different fitting attempts, suggesting outgassing occurs roughly symmetric about the orbital plane. Large values here would indicate strong asymmetry, active regions concentrated in one hemisphere or polar jets dominating gas production. The near-zero measurement argues against such extreme geometries, though modest asymmetries might exist below detection threshold. Fitting these parameters requires solving non-linear least squares problems, minimizing residuals across all observations while maintaining physical plausibility. The software explores parameter space systematically, testing various combinations, calculating predicted positions for each parameter set, comparing against observations, scoring fits by how well they reduce residuals. Convergence to optimal solution can require thousands of iterations. Numerical methods searching for minimum in multidimensional space, where each dimension represents one parameter to optimize. Correlations between parameters complicate the fitting. Changing radial acceleration affects predicted positions similarly to changing tangential acceleration in some geometric configurations, creating parameter degeneracies. Different parameter combinations producing similar predicted positions. Breaking these degeneracies requires observations spanning sufficient time and covering diverse geometry, different viewing angles and solar distances, sampling the parameter space from multiple perspectives. For 3 Ice/Atlas, The months-long observation arc provides adequate diversity. Inbound trajectory carrying the object through changing solar distances and viewing geometries. Astrometry sampling positions at different phase angles and elongations. This diversity constrains parameters more effectively than observations clustered in short time window. Geometric leverage, breaking degeneracies, allowing independent determination of multiple non-gravitational components. The perihelion prediction stabilizes as non-gravitational effects become well characterized. Early estimates placed perihelion around a certain date with uncertainties of weeks, distance uncertain within tens of millions of kilometers. Current predictions narrow to specific date within days, distance known to within 1,000,000 kilometers. Confidence high enough that observers plan perihelion period campaigns with specific targets for spectroscopy. Photometry, coma imaging during the close approach when activity should peak. The convergence brings satisfaction to orbit analysts, watching uncertainties shrink, predictions improve, models capture observations with increasing fidelity. But uncertainties never vanish entirely. Irreducible measurement noise and model limitations preventing perfect prediction. The object's actual position at perihelion will differ slightly from predicted position, residuals remaining even with best models, nature resisting complete mathematical capture. Temporal evolution of non-gravitational parameters receives investigation as data set permits. Do the parameters change with heliocentric distance as solar heating varies? Do they show time variation suggesting rotation modulation or changing active regions? Early analysis suggests possible strengthening of radial component as the object approaches the Sun, consistent with sublimation increasing at higher solar flux. Tangential component shows no clear trend, too uncertain to detect evolution if present. More sophisticated models incorporate functional forms describing how parameters vary with distance, maybe power law relationships, maybe exponential dependencies, forms motivated by sublimation physics. These models add complexity. Additional parameters describing parameter evolution, requiring more data to constrain but potentially providing better predictions and physical insight into how outgassing responds to changing conditions. The challenge lies in balancing model complexity against available data. Too simple, and the model misses real effects. Failing to capture behavior adequately, residuals remaining large, too complex, and the model overfits noise. Finding spurious patterns in random fluctuations. Predictions becoming unreliable when extrapolating beyond observed range. Statistical criteria help judge appropriate complexity, penalizing models for excessive parameters, favoring simplicity when additional terms provide minimal improvement. For 3I/Atlas, current consensus favors modest complexity, including non-gravitational acceleration terms with slow distance-dependent variation, enough to capture main effects without over-interpreting limited data. Future observations might justify more elaborate models, rotation modulation or multiple active regions, or time-varying production rates. But current data set supports only basic characterization. The refined trajectory allows calculating encounter geometry precisely, determining closest approach distances to planets, assessing gravitational perturbations from major bodies. Jupiter's influence peaks around a certain date when the object passes within several astronomical units, gravity altering trajectory by amounts exceeding non-gravitational effects during that period. Saturn contributes smaller perturbations. Other planets negligible. Including these perturbations in the model improves fits measurably. Planetary positions known precisely from ephemerides. Their gravitational effects calculable exactly. Only took development of least squares fitting by Gauss and Legendre in early 19th century to enable precise orbit determination from observations. Only took computer era to make a complex nonlinear fitting routine. Algorithms capable of handling dozens of parameters and thousands of observations converging to solutions in seconds rather than months of hand calculation. only took accumulation of observations across months to provide the baseline necessary for characterizing subtle non-gravitational effects distinguishable from gravitational dynamics, somewhere in the computational infrastructure supporting astronomical research. Software processes the latest observations of 3E/8LAS, incorporates positions into growing database, refits orbital parameters, updates predictions, generates ephemerides for upcoming nights. The calculations proceed automatically, algorithms executing deterministically, residuals decreasing incrementally as understanding improves. The object itself continues moving. Trajectory evolving under forces the models attempt to capture, mathematics approximating but never perfectly describing the physical reality unfolding in vacuum across millions of kilometers. Momentum and energy conserved exactly while human equations converge asymptotically toward descriptions that remain forever approximate. Useful but incomplete. Capturing essence while missing details that finer observations might someday reveal. The brightening curve flattens, peaks, begins its inevitable decline as 3I/8LAS passes perihelion and starts the long recession back toward interstellar space. Observations continue through the weeks following closest approach, tracking the object as it moves outward past Mars's orbit, solar flux diminishing, surface temperatures dropping, sublimation rates decreasing according to thermodynamic principles that link temperature to vapor pressure through exponential relationships. The activity persists longer than simple models predict. Thermal inertia and subsurface heat storage maintaining elevated temperatures even as solar distance increases. Hysteresis producing asymmetry where post-perihelion outgassing exceeds pre-perihelion levels at matched heliocentric distances. This behavior matches solar system comets, confirming that 3I/8LAS responds to heating similarly despite its interstellar origin. Physics operating identically regardless of which planetary system initially hosted the ice, now sublimating under our sun's radiation. Brightness fades steadily, magnitude increasing by fractions per week, the object becoming more challenging for smaller telescopes, requiring longer exposures to achieve adequate signal-to-noise. Large observatories continue monitoring when schedules permit, recognizing the opportunity will not recur. This one-time visitor receding permanently. Observations ending when the object fades below detection thresholds of even the largest mirrors. The astrometric measurements grow sparser as fewer facilities can detect the faint smudge against background stars. Data points that arrive daily during peak brightness now appear every few days, then weekly. Gaps in coverage expanding as the object dims. The orbital solution handles this gracefully. Months of dense observations during approach providing strong constraints. Late-time sparse measurements, refining outbound trajectory, but not changing fundamental parameters significantly. Non-gravitational acceleration continues operating even as the object dims beyond visibility. Outgassing persisting at low levels. Volatile inventory depleting gradually but not exhausted during the single perihelion passage. The acceleration magnitude decreases with solar distance as sublimation rates drop. Following predicted scaling relationships, confirming that models capturing the physics adequately if not perfectly, the last confirmed detection arrives from a major observatory using deep imaging, exposure times extending to minutes, stacking multiple frames to build sufficient signal. The object appears barely above background noise, position measurable but photometry uncertain, spectroscopy no longer feasible given the faintness. The detection confirms the orbit prediction, observed position matching predicted location within error bars, validation that non-gravitational parameters fitted during brighter phases still describe behavior accurately. After this detection, observations cease. Smaller telescopes lost the object weeks earlier. Medium aperture facilities gave up days ago. Even large observatories find the object too faint now. requiring exposure times that produce diminishing returns. Other targets offering better scientific return on precious telescope hours. Proposals to continue tracking get rejected. Resources allocated to brighter objects. More accessible targets. Science cases judged more compelling. The object continues outbound whether observed or not. Trajectory determined by momentum and forces that act independent of human attention. Sublimation likely persists at very low levels, molecules escaping too few to detect remotely, but sufficient to create tiny thrust. Acceleration continuing at levels below observational threshold, altering trajectory by amounts that accumulate over months and years, even though no measurements document the changes. Years from now, 3I/Atlas will cross Neptune's orbit outbound, moving through the realm where it was first detected. Distance now increasing instead of decreasing, velocity relative to Sun exceeding escape speed. Trajectory opening hyperbolically into interstellar space. No telescopes will observe this crossing, the object too faint, too far, too unremarkable to justify observing campaigns. The passage will occur unwitnessed, milestone marked only by calculations. Ephemeris tables noting the date when heliocentric distance surpasses 30 astronomical units. Decades hence, the object will exit the region dominated by solar gravity, reaching distances where other stars' gravitational influence begins competing with the Sun's. Trajectory bending gradually under combined effects of multiple stellar masses. The hyperbolic excess velocity carries it outward at several kilometers per second relative to the Sun, speed that will carry it light years in millennia. Distances where solar system membership becomes purely semantic. The object having returned to the interstellar medium from which it briefly emerged, centuries from now. If civilization maintains archives, researchers might revisit 3I/Atlas data, might apply improved analysis techniques, might extract insights that current methods missed, or the data might sit untouched, one more entry in astronomical databases. Observations preserved digitally but never examined again. The object having served its purpose in teaching about interstellar visitors, no compelling reason to revisit old datasets when new objects arrive regularly for study. The scientific return, though modest compared to some missions and observations, provides value through characterization of the third confirmed interstellar visitor. Composition measurements constrain formation environments in other planetary systems. Non-gravitational parameters document how these objects respond to solar heating. Trajectory determination enables statistical studies of interstellar object populations once sufficient sample accumulates. Each data point contributes to emerging understanding of galactic scale dynamics, planet formation around other stars, chemical inventories in different stellar neighborhoods. The outgassing that powered non-gravitational acceleration depleted volatile inventory measurably, perhaps removing several percent of initial ice mass during the months-long passage through the inner solar system. The remaining volatiles, protected under dust mantles or buried deep in the interior, will remain frozen as the object recedes into cold interstellar space. Temperatures dropping below sublimation thresholds. Activity ceasing permanently as solar flux becomes negligible. The surface, modified by this brief period of activity, carries scars from sublimation, pits where ice sublimated away, dust mantles thickened by non-volatile residue, thermal stress fractures from rapid heating and cooling. These features will remain unchanged for eons. The object lacking erosion mechanisms in interstellar space. Cosmic ray bombardment and micrometeorite impacts producing changes too slow to erase features on timescales less than millions of years. Only took months for 3I/Atlas to traverse observable solar system. From discovery beyond Jupiter to final detection receding past Mars, brief episode in cosmic timescales. One star's encounter in a journey that may span the galaxy over billions of years. Only took human civilization reaching technological maturity at precisely the moment when surveys became capable of detecting such visitors to document this particular passage. Coincidence of timing, allowing observations that would have been impossible a century earlier and may become routine a century hence. Somewhere outbound, accelerating gently under residual outgassing, thrust too weak now to detect. 3 I/Atlas continues its journey through vacuum and darkness, surface cooling toward equilibrium with cosmic microwave background radiation, coma dissipating as production rates drop below maintenance levels. The object returning to dormant state it maintained for however long it wandered between stars before this brief illumination. The trajectory carries it away, back into the sparse interstellar medium. Velocity vector pointing towards some future stellar encounter, perhaps thousands of years distant. Path determined by gravitational fields of stars it will pass near. None predictable from current observations. Future unknowable beyond statistical estimates of encounter rates and perturbation magnitudes. The observations end, the object continues. The archive preserves what was measured during those months when photons revealed motion and composition and the subtle forces that push without combustion through space. The data persists after the object fades from view. Observations archived in digital repositories maintained by institutions and international collaborations. Tables of numbers documenting positions and brightnesses and spectral measurements. Metadata recording which telescopes captured, which photons, on which nights, under which conditions. This archive constitutes the permanent scientific return from 3 I/Atlas's passage, information preserved independent of the object's continued existence, knowledge extracted from photons that can be analyzed repeatedly without depleting the source. The position measurements, hundreds or thousands depending on how final counts total, encode the trajectory through columns of right ascension and declination paired with observation times. Each row represents one measurement. One moment when the object's location was determined relative to background stars, precision varying from tens of milliarc seconds for best observations to several arc seconds for marginal detections near brightness limits. The timestamps, recorded in universal time coordinated to atomic clock precision, anchor each position to specific moment, allowing orbital calculations to integrate forces across the months-long observation arc. The uncertainties attached to each measurement reflect the observer's assessment of position accuracy. Estimates incorporating seeing conditions, detector noise, reference star catalog, uncertainties. Systematic effects from atmospheric refraction or telescope pointing errors. These uncertainties weight the observations during orbital fitting, precise measurements contributing more to parameter constraints than uncertain ones. Statistical framework handling inhomogeneous data quality properly, photometric data accumulates in separate tables, brightness measurements in various filter bands, observations documenting how reflected sunlight varied with time and viewing geometry. The measurements show scatter, intrinsic brightness variations mixing with measurement noise, rotation signatures, if present, buried in the scatter, secular trends of brightening toward perihelion and dimming afterward clearly visible above the noise. Magnitude scales convert to physical units through assumptions about albedo and phase function, but relative brightness changes remain model-independent, direct measurements of how much light the object reflected at different times. Spectroscopic data exists as arrays of wavelength versus flux, spectra capturing the molecular fingerprints in reflected sunlight, absorption and emission features identifying which compounds inhabited the coma. The data quality varies enormously. Deep exposures from large telescopes producing smooth spectra with high signal-to-noise, marginal detections showing mostly noise with hints of features barely distinguishable from statistical fluctuations. All preserve information, even noisy spectra, constraining what molecules could not have been present at levels the observations would have detected. These datasets enable retrospective analysis, future researchers investigating questions not considered during initial observations, techniques developed later applied to archival data, new insights emerging from old photons. The measurements themselves remain unchanged, but interpretation evolves, models improve, understanding deepens through reanalysis. What seemed unremarkable during initial study might reveal significance when examined with fresh perspective or combined with observations of other objects for comparison. The orbital elements, fitted to position measurements, summarize the trajectory compactly through 6 or 7 numbers, describing the ellipse or hyperbola the object followed through space. Semi-major axis negative for hyperbolic orbit, eccentricity exceeding unity, inclination describing tilt relative to ecliptic plane, longitude of ascending node and argument of perihelion specifying orientation in space. Perihelion time marking the moment of closest approach. Hyperbolic excess velocity encoding how fast the object escapes to infinity. These parameters, determined with uncertainties from the fitting process, provide sufficient information to reconstruct the object's position at any time, past or future, at least within the solar system where forces remain reasonably well characterized. Extrapolating to interstellar trajectories requires assumptions about perturbations from stellar encounters and galactic tides, uncertainties growing rapidly with time as small errors in initial conditions amplify exponentially in chaotic gravitational environment. The non-gravitational parameters, A1, A2, A3, join the orbital elements in characterizing motion, representing the average acceleration components that sublimation produced during the observation period. These parameters might not remain constant in future. Activity levels change as the object recedes. Sublimation ceases entirely beyond some heliocentric distance. Non-gravitational forces vanishing when surface temperatures drop below volatile phase transition thresholds. But during the observed interval, these parameters capture the average thrust effects, documenting how significantly outgassing perturbed the trajectory. Light curves exist as time series, brightness versus date, variations revealing rotation if periodicity can be extracted, secular trends showing activity evolution, scatter reflecting measurement precision and intrinsic variability. Future analysis might apply more sophisticated period-finding algorithms, time series techniques developed for other applications, extracting rotation signatures that initial analysis missed or confirming their absence if the object truly rotated pole on or exhibited no significant brightness variations. The archive grows slowly. Observers submitting data to central repositories weeks or months after observations, processing pipelines running, calibrations applied, final measurements delivered with documentation describing methodology and uncertainty estimates. Not all observations get archived immediately. Some remain in observers' local files indefinitely, published in papers but raw data never submitted to public repositories, limiting what future reanalysis can accomplish. Metadata accompanies the numbers, describing which telescope acquired which data using which instrument under which configuration, information necessary for interpreting measurements correctly, understanding systematic errors, assessing data quality. Without metadata, numbers lose context, measurements become ambiguous, utility for future research diminishes. Proper archival practice requires preserving context alongside data, ensuring future astronomers can understand what was measured and how. The papers published from 3 I/8less observations join the archive. Text and figures summarizing findings. Interpretations reflecting understanding at time of writing. References connecting to prior work and theoretical frameworks. These publications make the data discoverable, connect observations to scientific discourse, provide entry points for future researchers investigating interstellar objects or cometary physics or non-gravitational forces. Some results will endure. Facts that remain correct regardless of theoretical developments: the object's hyperbolic orbit, its detection dates, the measured positions and brightnesses. Other results might require revision as understanding advances. Composition estimates refined when better spectroscopic libraries become available. Non-gravitational parameter interpretations evolving as cometary activity models improve. Science proceeds through iterative refinement. Initial results providing foundation for later work that corrects and extends and occasionally overturns earlier conclusions. Only took decades of developing data standards and archive protocols to make astronomical data preservation routine rather than exceptional. Only took recognition that observations represent costly investments, telescope time precious, data retaining value long after initial analysis completes. Only took institutional commitment to maintain servers and databases and backup systems, ensuring data survival across technological changes and institutional reorganizations. Somewhere in the distributed network of astronomical archives, files containing 3I/Atlas observations reside on disk arrays and tape backups, checksums verifying data integrity, redundant copies protecting against hardware failures, metadata enabling search and retrieval, format conversions ensuring readability as software evolves. The data sits mostly dormant, accessed occasionally by researchers pursuing specific investigations. Bits preserved faithfully, whether consulted frequently or ignored for years. The archive offers permanence the object itself cannot claim. Measurements outlasting the photons that created them. Knowledge persisting independent of whether civilization continues observing sky, whether technology advances or declines, whether future astronomers care about this particular visitor or focus attention elsewhere. The numbers remain: light converted to data, motion compressed to parameters, one object's passage documented in tables and figures and text, small contribution to humanity's accumulated understanding of the universe. Minor addition to the catalog of what has been observed and measured and recorded for potential use by minds not yet developed, asking questions not yet formulated about patterns not yet recognized in the vast complexity that surrounds and exceeds and ultimately encompasses all endeavors to quantify and comprehend. The observations fade into memory and archive, the object itself receding beyond what any current telescope can recover. Outbound trajectory carrying it through the outer solar system at several kilometers per second. Velocity sufficient to escape the sun's gravity permanently. Path determined by the accumulated momentum from formation and ejection and the long drift through interstellar space and the brief months of solar perturbation. The forces that pushed it: sublimation thrust measured in micronewtons, radiation pressure even more gentle, gravitational tugs from planets that never came particularly close. All these diminish now with distance, becoming negligible against the larger canvas of galactic dynamics. Stellar winds and spiral arm density waves, and the slow gravitational tide from the galaxy's mass distribution, somewhere far from human view. 3I/Atlas continues, surface silent again. Volatiles locked in frost that will not sublime at the cold temperatures of interstellar space. No coma, no thrust, no acceleration beyond what distant stars provide through their gravitational influence. The object returns to the state it maintained for however long it wandered before encountering our sun, dark and quiet, carrying its composition and structure and history toward futures no model predicts in detail. Timescales extending beyond the lifetimes of civilizations, perhaps beyond the lifetime of records documenting its brief passage through one minor planetary system orbiting one unremarkable star. The knowledge remains archived. Observations preserved in the formats and media current technology provides, subject to decay that careful stewardship might prevent or that neglect would accelerate. The permanence of data always conditional on continued maintenance. Institutions persisting. Standards evolving while preserving backward compatibility. Someone somewhere deciding these particular measurements deserve preservation even as storage fills with observations of thousands of other objects competing for the same archive space and maintenance attention. In time, perhaps, the measurements will inform statistical studies of interstellar object populations, this one visitor combining with dozens or hundreds of others, sample sizes growing until patterns emerge with confidence, distributions of composition and size and trajectory becoming clear, the individual fading into the collective understanding of what wanders between stars, how often such objects pass, what they reveal about planet formation across the galaxy's diverse stellar environments and epochs. For now, the story ends with fading, with silence, with data tables settling into archives, with the object itself receding into darkness, pushed gently by forces too subtle to name in everyday language, but describable precisely through equations capturing momentum transfer at molecular scales. Physics that operates whether observed or not, whether understood or mysterious, whether anyone watches or the universe proceeds unwitnessed through its deterministic evolution from initial conditions toward futures that remain. Despite all calculation, fundamentally uncertain in their details while statistically predictable in their broad patterns, the gentle forces continue their work somewhere in the dark, pushing what remains pushable, leaving traces in trajectories and archives, connecting past to present to future through conservation laws and data preservation, and the slow accumulation of understanding that each observation, each measurement, each preserved photon contributes to the ever-incomplete but ever-growing map of what exists and how it moves through the vast and patient universe,